Well, it's a new engine, and it uses, besides the known principles of internal combustion and turbomachinery, shock waves to transmit energy from
a spinning disc, no pistons, no rotors, just shock waves doing the compression. That's the promise of the wave disc engine, one of the strangest machines ever built for combustion. It sounds like a lab stunt, yet it was designed, machined, tested, and it worked. In this video, we'll unpack how pressure waves squeeze air in microseconds, how fuel lights inside tiny channels. Then we'll face the real-world hurdles that stopped it, and why the design can cut friction and heat loss from the start. If you love wild engineering, tap like, subscribe, and let's dive in together right now. Why normal engines lose so much. A classic internal combustion engine is a crowded machine. Pistons slide in cylinders, rings scrape oil, valves snap open and shut. A camshaft and a timing chain keep everything in sync. Then you add pumps, belts, and other helpers just to keep it alive. Every one of those parts steals energy. Some losses come from friction, where solid parts rub on solid parts. Other losses come from heat, because the air and fuel sit against metal walls while they are being compressed. That gives heat time to leak away before it can do useful work. Rotary engines can look simpler, but they still depend on seals sliding along a housing, so friction and leakage stay in the picture. This is why engineers keep chasing the same dream: fewer moving parts, faster cycles, and less time for heat to escape. That dream is exactly where the wave disc engine steps in. The disc still turns on bearings, but the big sliding surfaces disappear. And because the concept was aimed at running at a steady speed, it tries to let gas dynamics do the compression job that pistons normally do. It fit naturally as a generator engine for hybrids, where constant operation is easier to optimize. The disc and its hidden passages. Instead of cylinders, the wave disc engine uses a flat disc that spins inside a close-fitting housing. Carved into the disc are many narrow channels, like spokes running from near the center toward the outer edge. As the disc rotates, the ends of these channels line up with fixed openings in the housing. For a brief moment, one opening becomes the intake. A moment later, another opening becomes the fuel port. Later still, another opening becomes the exhaust. The disc is doing the timing simply by turning. This idea grew out of a related device called a wave rotor, also known as a pressure exchanger. In that world, engineers learned that pressure waves can move energy from one gas stream to another very quickly. The wave disc takes that same wave physics and wraps it into a compact, rotating package. Each channel acts like a tiny tube where gas can rush in, bounce, compress, burn, and leave, all without a piston sweeping up and down. Think of the housing as a stationary mask with windows cut into it. As the disc spins under that mask, each channel meets those windows in a strict order. Fresh air in. A brief, sealed moment for the wave to build, fuel added, then exhaust out. There are no springs, tappets, or cam lobes doing the timing. The geometry is the valve train. Because there are many channels, the engine does not rely on one big bang per cycle. It relies on many small, rapid events spread around the disc. That is why it can feel less like a clunky machine and more like a controlled rhythm. The trick is making sure every alignment happens at exactly the right time, because the waves do not forgive sloppy timing. Here's the part that sounds unreal until you picture it. When fresh air enters a channel, it does not drift in quietly. Compression by shock waves. It rushes in and forms a pressure wave that travels down the passage. The far end of the channel is effectively closed at the right moment, so the wave reflects. When that reflected wave meets the incoming gas, pressure spikes. That spike is the compression stroke, but it happens in microseconds, not milliseconds. In other words, the gas gets squeezed by a moving wave front, not by moving metal. This wave compression is powerful, but it is also picky. If the disc rotates too slowly, the wave arrives late, and the cycle loses its punch. If the disc rotates too fast, the wave may not fully form before the ports shift, and the whole pattern falls apart. Small timing errors can also cause backflow, where a wave bounces the wrong way and pushes hot exhaust back towards the intake. That would contaminate the next charge and kill efficiency. A team at Michigan State University, led by Dr. Norbert Mueller, spent years modeling these wave interactions. They tuned channel length, cross-section, and port timing as a single system. They used simulations, then hardware tests, to find stable operating windows where the waves compress the charge cleanly and repeatably. When they hit that window, the disc behaved less like an engine with moving parts, and more like a carefully timed acoustic instrument. Burn, blowdown, and the drumbeat of power. Once the air is compressed by the reflected wave, fuel can be injected into that dense, hot charge. Then, as the disc continues to rotate, the same channel lines up with an exhaust opening. Combustion begins quickly because the conditions are already intense. The burned gases rush out in a sharp pulse. That pulse is not a flaw, it is part of the design. With dozens of channels around the disc, these pulses overlap in time and create a more continuous delivery of power. Speed is the secret advantage here. In a piston engine, compression and burning take long enough that heat has time to soak into the cylinder walls. That wasted heat is one of the biggest efficiency killers in combustion. In the wave disc, the key events happen so fast that less heat can escape during the crucial moments. More of the energy stays in the gas, and that energy can be turned into useful work. The pulsing exhaust also opened up a clever idea. Engineers explored pairing the disc with a small turbine to harvest extra energy from those bursts, almost like a tiny jet stage bolted on. That could push total system efficiency even higher. It would turn the engine into a hybrid of concepts, part pressure wave machine, part combustion chamber, and part energy recovery device. Why engineers got excited? When the wave timing is right, the performance numbers can look shocking. The Vision was a compact unit that makes power steadily, with fewer moving pieces to wear out. Prototype reports often pointed to thermal efficiency near 60%. That is a huge figure for a small combustion device. Many road car gasoline engines operate far below that, especially in stop-and-go driving. A wave disc running at its sweet spot could approach the territory people usually reserve for advanced systems, like large diesels or fuel cells. Size was the other headline. Designs aimed at hybrid cars were described as extremely compact, with some concepts claiming around 1/5 the size and weight of a comparable piston unit. That matters most in a range extender role. Instead of directly driving wheels, the engine would spin a generator at a constant speed and feed an electric drivetrain. Small engines usually hate partial load, but a range extender can be locked at its best operating point. That is where the wave disc idea shines. Fuel flexibility made it even more interesting. The cycle can be adapted to run on gasoline, diesel, ethanol, or hydrogen. Hydrogen in particular burns fast, which matches the rapid wave-driven process. Because of that efficiency and steady operation, some projections suggested very large reductions in carbon dioxide for the same delivered electricity, sometimes quoted as high as 90% versus a typical gasoline setup. Even if real-world numbers vary, the direction was clear. What stopped it from taking over? For all its elegance, the wave disc engine ran into brutal realities. First was manufacturing, compact power with fewer losses and cleaner options. The channels in the disc must be shaped with extreme accuracy. If one channel is slightly off in length, depth, or edge profile, the wave timing shifts. If many channels vary, the engine becomes unstable or weak. Making those fine passages is possible in a lab, but producing them cheaply and consistently at scale is a different challenge. Heat was another enemy. The disc experiences repeated bursts of hot gas while spinning at high speed. The housing has to keep tight clearances, so the ports line up cleanly, even as materials expand and contract. Too much expansion can ruin sealing and timing. Too little tolerance can lead to rubbing and damage. Then comes lubrication and sealing. Without pistons splashing oil everywhere, bearings and seals need a deliberate strategy. They also have to survive high temperatures and pressure pulses. Finally, timing and business timing collided. Investment in strange new combustion ideas dried up, even if the ideas were efficient. As this work was developing, the auto world pushed hard toward full battery electric cars. The wave disc proved the concept, but it never became a mass product. Still, it may not be a dead end. Drones could revive interest, especially if hydrogen becomes easier to store and distribute. Engines usually evolve by small steps. The wave disc tried a leap. Portable generators and hybrid systems that need light, steady power. It replaced the slow mechanical squeeze with a fast, invisible squeeze made of pressure waves. It also demanded precision, cooling, and funding that were hard to secure at the time. That one shift cut friction, trapped heat, and packed power into a tiny space. But the idea still sits on the shelf, waiting for the right moment, the right fuel, and the right manufacturing method. Tell me in the comments, would you trust an engine powered by shock waves? Thanks for watching, and I'll see you next time.